Oh, there we go. Let me see if I can get this rigged up here. So sorry, guys. I think we've got Elias standing by. That's Elias. Welcome.
Thank you. Thank you.
Well,
So nice to see you.
Yeah, nice to see you too. Thank you for taking the time to be one of our moderators.
Sure. So
one of our presenters, I should say.
Presenters, yeah.
Yeah. No, I'm the moderator. You're the presenter. My bad. I'm sorry.
Okay.
We'll give people a moment to hop in here.
Sure.
We'll get going here in about 3 minutes, and let everybody say hello.
All right.
So are you in Germany now? Is that where you're at now?
I'm in Germany, yeah, right. So it's 6:15 in the evening.
Oh, so you're about ready to call it a day then?
Well, yeah, I am. But whatever. I'll spend another few hours watching the other talks. There's still quite some exciting content ahead.
Excellent. Okay. Well, that sounds great. So for those of you who are, what's that? I'm sorry.
I said in the worst case, then I have to watch the recordings.
Yeah. By the way, that's I'm glad that you said that. All of these are being recorded. Every one of these sessions, as people are hopping in, if there's a particular session that you had to choose between, like maybe there's a couple of them and you had to choose one over the other, all of these are being recorded and you'll be able to go back and watch them later. But we know you're going to be watching Elias over and over and over again because he's going to be a font of information, right? Hey, Mark, welcome to the session. Glad you're here. Give people a few moments to a couple more minutes to hop in here. Thanks, everybody. Another Mark. Hey, Mark. Thank you to all of you who are here for joining us at SaltConf virtually everywhere. SaltConf20, kind of a weird year, as I'm sure you're aware. Hey, Eric, thanks for hopping into the session. Glad you're here. So we're going to have a 10-minute Q&A at the end of this, and there's a couple of things you can do here as you're jumping in. If you would like to type your question in the chat, you're more than welcome to do so, and I'll read your question for you. Or there's a thing at the top of your screen that says share audio and video. You'll have to hit that tab, as Ermi did, and I'm going to clear you out there, Mr. Benjamin. And if you hit that tab, then what that'll do, I'll turn that on, and your video and your audio will come on, and you can talk to Elias directly. So, and we'll do that near the end of the session. So it looks like we got some people filing in, and we're about ready to go. As you're all getting comfy here, the topic today is why SaltStack is automation for the future. And hey, Chris, I thought you had a real question for him. I'm sorry, man. So why SaltStack is automation for the future? So everyone, please give a warm virtual Sean. I never thought I would see Jimmy Chung at a tech conference. Used to listen to him while getting ready for class in Provo. Yeah, that's awesome. Well, I got to be honest with you, Sean. I never thought I would see me at a tech conference either, considering I'm easily the dumbest person in this room, without a doubt. But glad you're here, Sean. It's good to see you. So anyway, if you have any questions at all, please don't hesitate to request to share your audio and video. And we'll get to those near the end of the session here. We'll have about a 10-15 minute Q&A. Elias Probst, why don't you tell us a little bit about yourself before we get into what we're talking about today?
Yeah, so thank you for the warm welcome. Happy to see you all here. Yeah, so maybe first a little bit of me. Yeah, as you said, my name is Elias Probst. I live in southwestern Germany, close to Stuttgart. And I've been doing Linux-related open source projects now basically for the majority of my life, more than 20 years now. And especially in all things around system life cycles, OS management, and the low-level user-land stuff within Linux systems. So a lot of the layer between the kernel and the actual applications is what intrigued my interest. But also for a significant amount of time, I've been active in the KDE community, which previously Dirk and Tom already talked about a lot in their open source talk. Yeah, so I've been active in various open source environments during the last 2 decades, and mostly with figuring out bugs, reproducing bugs, reporting bugs, all around making applications work better, stringent, bug-free, those kind of things. But also in projects like Gentoo Linux, helping with packaging and keeping packets up to date and these things. So far about me. My job is at SSC-Services. That's an IT service provider in Germany, also close to Stuttgart, located in Böblingen. SSC was founded in 1998. I think that's the same year as VMware was founded. And it has its roots in the automotive and supplier world. Its core mission is to create connections in every way. This might be technical processes, collaboration, and so on and so forth between organizations through software, systems, consulting, services. So one of the core products of SSC is called Swan, which is a software used by the automotive industry to exchange project data, construction data, and all this based on security policies, scanning project data, converting CAD files, these kind of things. Automated Reality is a sub-brand within SSC, which was recently established, and it focuses on all aspects of automation. This also includes our Solstec partnership and activities. We are a Solstec partner since nearly a year now, and we are so far the only Solstec partner within Germany. So for today's talk, let me say first, I'll begin, and it won't have to do much with Solstec in the beginning. It's about the drive for automation, what drives people to automate. And later we'll look into, okay, what is Solstec actually doing and what will be the future of Solstec in this ever-developing IT world. So first I want to talk about the history of computer systems. There are quite a few interesting things here, and the configuration and management and how all this came and where it'll go and what Solstec's role in all this has been and will or might be. So let's first do a little time travel way back into the past and to the very beginning of computers. So let's travel to 100 BC. So in 1901, an archaeologist retrieved this item from the sea off the coast of a Greek island called Antikythera. And it's the oldest known example of a complex mechanical computer and allowed to do advanced predictions of astronomical events. Well, it certainly has its flaws, and due to the back then not quite precise ancient knowledge of planetary movements, it didn't really work out, but it's still a fascinating artifact because it's a testimony to humanity's desire to build devices and automatisms to satisfy their need to somehow perpetuate the procedures they have and their knowledge into machines instead of transporting it via written or spoken prose, which can be misinterpreted and is hard to reuse. So yeah, this was surely found in salty water, but it's not related to SaltStack. So this mechanism, although it was back then only usable by knowledgeable users, is a very simple computer from today's point of view. It's completely mechanical. It doesn't change its behavior during runtime at all. Has no way to configure it. You simply turn it and look at the output. And its only failure scenario is of mechanical nature. And sometimes I wish debugging complex bugs, this would still be the way we work. Just look at a thing and figure out which wheel turned wrong. Well, I guess we haven't this anymore. So let's jump forward 1,800 years. In 16703, Gottfried Wilhelm Leibniz, a German mathematician and scientist, presented his first step reckoner at the Royal Society in London. And it was capable of basic arithmetic operations for up to 16 digits actually. A later iteration, I think, even went to 20. But it lacked capabilities for logical operations, which we take for granted in nowadays computers. And Leibniz built a few iterations of this machine, and this got him quite some attention in the scientific community. But it was never really widely adopted because it had a major flaw, and this was that it couldn't do the carry operation to actually count along from 9 to 10 or from 99 to 100 properly without manual intervention. And this made it quite a bit difficult and error-prone to work with. And Leibniz later also invested a lot of research into solving this problem, but really never got it working as expected. Furthermore, it also took a lot of time to build these things. In 2004, two German engineers took on the task to build a replica of this, and even used modern tools and methods such as CAD/CAM and CNC and whatever. And they ended up taking more than 1,500 hours for this piece. And if you imagine the tools available back then, what huge amounts of time it must have taken to produce those things. So they were probably really expensive and no one could really afford them. But still, Leibniz had the spirit that a lot of us drives today in the Solstec and also in the wider automation and IT community. And this becomes quite apparent through this quote by him. "It is unworthy to waste the time of excellent people with servile calculations, because if a machine is used, even the simples can write down the results safely." So our motivations nowadays might be a little more nuanced and refined, and but still it reflects the drive to use the potential of the human brain to its fullest and leave simple and mundane tasks to machines. So this step reckoner, basically it was a hardware where the hardware is to program and has a limited set of capabilities. It can be configured before execution to define the kind of operation: multiplication, subtraction, division, and addition. It needs input, but due to its lack of a proper carry operator, actually its behavior can change during runtime if you don't make use of it properly. So forward another 265 years, and what might look like a scene from Fritz Lang's iconic movie Metropolis is actually the first working proper mechanical computer in the world. This was built by Konrad Zuse, and it's called the C1. It was the first freely programmable computer in the world. It used Boolean logic, it had support for floating point numbers, and its mechanical motor-driven mechanism could even read input from a punched tape. This was quite an achievement. But due to the Second World War, the development of the C1 remained isolated to Germany and didn't have any real direct influence on the development of future computers in England and the USA. But it was still the first to implement all the fundamental concepts and features of a modern computer that we still take for granted. So Zuse started thinking about a computer when he worked as a structural engineer at an aircraft manufacturer. And he had to do a lot of manual complex calculations, and he couldn't stand it anymore to handle them all manually. And this drove him that far that he actually quit this job and went on to work on this computer in full time. And just like the predecessors building the other computers I just talked about, Zuse was obsessed with the idea of improving our lives by augmenting the human intelligence with automated technology, controlling traffic lights to allow a green wave, or mechanizing the development of photofilms, or even recent developments, which we see now in modern cars with automated high beam and low beam lights. They are actually based on a patent of Konrad Zuse, and it simply couldn't be implemented back then because the technology required for this wasn't there yet, LED lighting especially. But whatever Zuse looked at, he saw the potential for improvement, for automation, for using machines. And throughout his whole life, he contributed a lot to mathematics, physics, computer science, and even arts. And if you look, for example, at modern programming languages, one thing a lot of them, especially in the functional community, are based on are his ideas of Plancalcul. This was one of the first languages basically invented. So the architecture of the C1 was not only groundbreaking, but it also introduced all the concepts of software we take now for granted because it was freely programmable. And its fundamental architecture is still what we see today in computers based on the von Neumann architectural principles with all the components that it has. So even though modern computers have their roots in many similar projects by other scientists and mathematicians and other bright minds of this time, the C1 was the first actually working example of such a machine, and was developed in complete isolation from the others due to the war. And all the others were also developed behind military doors, behind closed doors. For example, the ENIAC, which was used by the Americans to accelerate the calculations necessary for the development of the atomic bomb. So the year 1947 actually marks quite an inflection point in computing. This was when the first working transistor was built by scientists in the Bell Labs, and the introduction of the transistor kickstarted an unprecedented technological revolution. The global production of transistors per second is now higher than the annual output only 20 years ago. So we build trillions of them every minute. And the transistor is also the point basically where the software journey really starts. Because the ever-increasing compute power provided by transistor-based computers allows now basically to build everything we can imagine in software as a reproducible, repeatable, and changeable piece of code. And this resulted in a huge boost of software systems, which aren't just a single linear piece of code on a punched tape, and we walk over into the computer lab and feed it into a computer and awaken the beast. This all was now not necessary anymore. Instead, we had now continuously running systems, and their process execution was handled basically as a software problem. And they read and persisted their data again to reliable storage, and even then soon learned to talk to each other using networks. And also another effect, which I previously mentioned, is with the transistor, we lost the capability for mechanical observability. So we can't derive a system state anymore from purely a physical inspection, but it needed to happen on a software level from now. And this is still what we have to do now, and is a huge field in running systems, probably. So throughout the next decades, computers became bigger, more powerful, more efficient, cheaper. I mean, look at this bang, that's 64K diskette for only $2,000. I mean, what can you expect? And finally, also they became consumer accessible with computers like the C64 or Amiga 500 or Apple II, and those were really consumer accessible devices. So this was the age when the broad adoption of computers had arrived by the mid-late 80s. And this was also one of the catalysts for an extraordinary development. Linux. And I think I certainly won't have to explain anyone nowadays what Linux is, but I still want to highlight the extraordinarity of things that had to happen at the right time back then to allow for its unbelievable success. Because it was the culmination of the existence of relatively cheap hardware based on the IBM PC standard. So actually Linus built his first iterations of Linux on, I think, a 286 or 386. And also the drive for free and open software that is free from commercial and proprietary restrictions. Because one of the motivations of Linus was the restrictions around using Minix that were used in the academic field to teach about operating systems. Yeah. And also a third factor that was just there at the right time was the userland tools provided by the GNU project around Richard Stallman, because they allowed basically Linux to focus on the kernel itself, and for them first not have to focus on the userland aspects. But the spirit behind Linux was not only the driver of a lot of later open data projects in the spirit of Wikipedia and OpenStreetMap and similar initiatives, but it was also the foundation that allowed companies like Google or Amazon and even their nowadays existing cloud platforms to exist in the first place, because Linux was capable of running on standard x86 hardware. It was freely available, it was adaptable, and had by then a huge user base in the community, which allowed those companies to adapt it to their needs and use it as a base for their enterprises. And what was back then a niche has now become mainstream, especially since the last, I would say, 5 to 10 years. It is now regular that software is developed in the open as free software. There's community building around software projects. We see this in the CNCF, we see this in SaltStack. It's always a matter of having a proper community around the software. The whole collaborative working models is also something that spilled over into actually the regular working world, how people collaborate, because now they have those tools that were established in those communities. And also, as also Dirk Handel previously mentioned, enterprises adopting open source as part of their key infrastructure and also being major contributors to open source projects. And finally, this whole idea and spirit is also the foundation of what SaltStack is built upon, what Tom Hatch led to start SaltStack. First, he didn't start it for commercial reasons, but simply because he wanted to scratch an itch. So let's have a look at the evolution of systems from this time. So first, as always, we need a piece of hardware. Back then, cheap IBM PCs. On top of that, we need an OS to run. This could be BSD, Windows, Linux. We're looking at Linux right now. And on top of that, we need the userland, because the kernel itself is relatively worthless. It won't do much on its own. So we need some userland. This being primarily applications and the libraries, but also configurations, because the configuration controls the default behavior for the environment of a system and how those applications will run. And this is also where it gets interesting, because the OS kernel itself, as well as the whole userland, somehow needs to find its way into a system. And in the old days of computing, first you built hardware, which was the program. There was nothing to change. You built it, and that's the way it worked. Then later on, it was basically programmable. You used a punched tape, and this was your OS and program at the same time. But really, the flexibility now provided with those kind of systems required that there had to be workflows around how to properly deploy and update applications. And this led to the development of package management. There was a previous forms quite early developed by IBM on its 360 systems, but really the way we get to use it was made popular by Linux. And it uses a central, mostly online package repository, providing a wide variety of up-to-date packages and dependencies. And the manager ensures that software can be easily installed and removed with just a single command, and everything's kept up to date. And to some extent, those package managers also provide a working default configuration for the applications. But that's only half the truth, because while this works great as a manual process for a single system, there was not much in those tools to reuse the system blueprint and restoring it on another system into a defined state, replicating it across a vast number of systems, or building variations of it with slight difference in a really proper, centrally managed way. And there were problems to be solved around this to have fully working systems, such as user management, providing configuration files, the management of secrets and credentials, but also being in control of the wider whole system lifecycle. And this is where early config management solutions came to play. They provided a layer on top of those systems and mechanisms to fulfill some of those needs in terms of reusing system definitions and configurations across systems. But they still lacked some capabilities, because a typical IT infrastructure is usually a little more than just a single server. So systems were broken up into multiple ones to fulfill specific roles, such as the famous 3-tier architecture, where you have a central application server fronted by a web server, backed by a database or storage server. So this meant for an application to properly work, we had to have more than one system that talk to each other and work with each other. And soon then they were scaled horizontally for various reasons, for either increasing the overall performance or also achieving higher availability through failover mechanisms. And this not only meant having to apply changes to an ever-increasing number of systems, but also ensuring that the dependencies between those are handled correctly. Which system can be online at which point? Running the application server depends on a properly working database server. The web server can't work without the application server, and so on and so forth. And an ever-increasing heterogeneity of various operating systems, applications, and services showed the need for an abstraction layer here. And also, that's not where it stopped, because at a certain scale, we also need to somehow handle the vast number of hardware. The hardware layer also needed to be taken care of, meant either managing it through a BMC like Dell iDRAC or HP ILO and those kind of things, handling firmware updates, or configuring low-level stuff such as RAID controllers, RAID setups. And also then a certain company popularized a concept called virtualization. I feel a few people here might know what I'm talking about. But this suddenly meant we are able to run more than a single piece of system on a single piece of hardware. So this way to run multiple systems on a single piece of hardware allowed for better resource utilization and also easier workload migration between physical systems. So if I need to take one system out for maintenance, I could migrate the workload to any other ones. And also with this growth of things that a single person could handle, there were then complexities around managing users accessing those systems. So which admins get to access which parts of such a complex infrastructure. Then we saw early pipelines like Jenkins and these kind of things that took care of testing and building deployment artifacts. And more during the last years, APIs started to emerge as the primary way to interact with infrastructure and services. And also for on-premises infrastructures, the move towards software-driven infrastructure meant that we had to somehow deal with often legacy hardware in terms of networking hardware like routers or switches, firewalls. These kind of things need to be managed in some way as well. And then ever increasing also integrating cloud resources into the whole infrastructure. So this ever increasing complexity and diversity of solution and more challenging external requirements this called for a solution to prevent that all those various technologies and dependencies and responsibilities were hidden in silos, detached from each other within a company. There needed to be a way to centrally handle those, to have a single point of entry and control for those. And that's where SaltStack shines. So SaltStack is very unique in the way it is built. So in the very beginning, many, and even Tom himself, saw SaltStack just as yet another config management tool, focusing on the old idea of I need to deploy configurations, packages, users, whatever, onto systems. But actually, the way it was built, it turned out to be far more than that. And config management was just a single problem domain that it would be able to tackle. And the fundamental strength of SaltStack is its system-agnostic communication model. It, from a very high perspective, just deals with generic jobs that it issues that are then pulled from its queue, and events that it takes in and processes. But it does not really care about the content of those jobs and events. And the whole thing is fueled by a very rich toolbox of modules. Previously, in the open source presentation from Dirk and Tom, they called it a box of Legos, and I tend to agree, because you have just rough building blocks, and you can build whatever you want out of this building blocks, and build it in whatever way you need it to have a central point of managing your IT infrastructure across silos, various technologies, operating systems, cloud providers, or lifecycle management solutions and pipelines and these kind of things. So SaltStack is built to act as a central and neutral control plane in such environments. And this is also why I have high hopes for its future, because it's not opinionated, it's agnostic. It doesn't really care about the details below, which can be just put together in the way that it's needed. So if we look at the way operating systems have been managed in the past, there was always the pain of ensuring that a mutable system, a system that changes over time due to updates, config changes, whatever, matches the defined state from a config management. And the complexity of handling the transition between a given and a defined state is still today one of the most complex aspects of managing those kind of systems, because one first needs to deal with all kind of possibilities how the system could look like, behave like, and then shrink it down to a single point of where you atomically then change your state to your defined state. And this involves a lot of complexity in the way those systems are traditionally built. And on the application level, container orchestrations like Kubernetes or HashiCorp Nomad emerged, and they handle the reconciliation of defined state as a control layer application logic problems. So you throw a definition at them and they will ensure that the defined state is reconciliated, but not within a system, but within the application state, meaning the actual controller components of the container orchestration. And they also provide a rich bundle of other entities that are required to operate services, such as storage, networking, resource management, role-based access control, deployment logics, lifecycle management. Those things are all bundled up together in this container orchestration solutions. And if one runs an application in such an environment, suddenly those things that one had to be dealt with in traditional immutable systems are a thing of the past. There are other complexities, there are other downsides possibly, There are the challenges, but those things are a thing of the past. But still, those components of Kubernetes and their low storage layers and their low API layers and all service components of Kubernetes itself still need to run somewhere. There is still a base OS somewhere. And this is also something that won't go away easily. It's still something that has to be managed. But even there, things might or are changing. So on the base OS level, there are concepts of immutable systems, which in parts act a bit like a container. This means a system that's running will never change its state. It will switch its environment. We have there immutable atomic systems like NixOS or Red Hat's Atomic, formerly CoreOS Linux or Container Linux. And those are those kind of immutable base operating systems. And some of them, for example, NixOS or the GUIX distribution from the GNU project, even provide a holistic configuration management built into the actual system management. So even this problem is solved within the operating system there. And looking at those things, this means in this area, the traditional config management solutions, also the ones provided by Solstec, might be sooner or later obsolete. And if you look, for example, at the hardware level, it increasingly becomes more a job of managing cloud resources than instead of managing actual hardware. And if you look at this, this is also something where traditional purpose-built, opinionated solutions in this area will have a hard time adopting. They are purpose-built and won't easily change to work with those new requirements. So the future of SaltStack, in my opinion, is not so much about solving those traditional problems. They might be there for the time being. They might fade out sooner or later, but it's about bridging the gaps between all those ecosystems, different APIs, different toolings, different cloud providers. There's a vast selection of solutions how to run systems nowadays. And still, it's not that we have one single entry point, one single point of control for those. And this is where SaltStack will have a place to shine, because due to its agnostic model, due to its rich toolbox, it will be able to talk to all kind of things that there are and that there might be. And with the adoption of the POP or item concepts that parts of the SaltStack community are working on now, that Tom Hatch started, I think, nearly 2 years ago, and those concepts spilling more and more over into SaltStack will even make it possible that SaltStack is not only looked at as a part of, we have master infrastructure and we have the minions communicating with the masters, but that it also becomes a solution to solve problems on a programmatic level. So it could become part of applications, pipelines, or developer workflows. And we'll see huge gains there because of this rich toolbox that's already there and can be reused. So I see a bright future of SaltStack due to its neutrality, due to its rich toolbox, and due to the way it can adapt to whatever the future will bring. That's my core message that I want to close with for now. So thank you, and if you have any questions, ideas to be discussed, you're welcome.
First of all, let's give some virtual applause to Elias here, mate. Cheers.
Thank you.
It was fantastic. So yeah, we do have some time for a short Q&A session. If there's any questions, there's a couple of ways you can deliver those. You can either A, type it in the chat here and I'll relay them to Elias, or you can hit the share audio and video little tab at the top of your screen, right up there, and then it'll let me know that you want to talk, and then I'll just let you in. So pretty simple stuff. Anyone? Bueller? No questions for Elias? It was great to see all of you in the hopping into the session, by the way. Shout out to Wayne and Darko and Mark and Mike. Good to see all of you. Is that going to be it? All right. Well, if there's no questions, we'll give you guys a little bit of extra time. Remember, your next session is going to be starting at about 15 minutes past the hour, and we'll see you on the next one. Thanks, everybody, and shout out again to Elias. Thank you, Elias.
Thank you, everyone. See you.
All right. See you later.
Bye-bye.